For years, we've all been chasing scale, right? Thinking that bigger models and more data would eventually solve all of AI's problems. But we're hitting a wall. And the reason our most advanced models are failing isn't about scale at all. It's about math. Today, we're exposing the fatal geometric flaw that they simply can't escape.
You know the drill. You've got a massive billion-parameter transformer trained on practically the entire internet, and it still hallucinates, it gets tangled up in simple hierarchical reasoning, and it just breaks the second it sees data it wasn't explicitly trained on. So what is really going on here?
Well, the core argument of this new research is pretty profound. The problem isn't something we can just engineer our way out of with more GPUs. The flaw is foundational. It's baked right into the mathematical space, the Euclidean space, that almost all of our models live in.
And you've got to understand, these aren't just random, isolated bugs. They're all symptoms of the same underlying disease. You've got semantic collapse, where your model just can't grasp that a poodle is different from a golden retriever deep down in a hierarchy. You've got oversquashing, where critical information just vanishes in deep networks, brittle generalization, and of course, constant hallucinations. These are all direct results of a geometric bottleneck.
Okay, so if those are the symptoms, where's the actual proof? Well, the smoking gun isn't some fuzzy hypothesis. It's a mathematical certainty that traps our models in what you can only call a Euclidean prison.
This is it. It's called the Geometric Capacity Bottleneck. And what it does is formalize the problem. It proves that it is mathematically impossible to accurately represent complex hierarchical data, which grows exponentially, inside a flat Euclidean space. Why? Because the volume of that space only grows polynomially. You are literally trying to fit an ocean into a bucket.
And this right here just lays it all out, doesn't it? Think about your data, things like language, biology, any kind of hierarchy. It branches out like a tree, growing exponentially. But the Euclidean space you're cramming it into, that grows like a simple ball, polynomially. The container is just fundamentally the wrong shape for what you're trying to put in it. It's a mathematical guarantee of distortion.
And here it is, the verdict, straight from peer-reviewed mathematics. Theorem 3.1 from the paper proves it, no ambiguity. To embed a complex tree without totally destroying its structure, you're left with two terrible choices. Either your Euclidean space needs an exponential number of dimensions, which is computationally a non-starter, or you accept catastrophic distortion, where all the rich, meaningful relationships in your data just get crushed together. There is no third option.
Okay, so if Euclidean geometry is the prison, how the heck do we break out? This is where the paper proposes something truly radical, the phenomenal manifold hypothesis. And this isn't just a patch. It's a completely new theory for how intelligent structures can even emerge in the first place.
Right at the heart of all this is this core equation. It describes the metric. You can think of it as the ruler for a whole new kind of geometric space for intelligence. It's made of two parts. First, you've got the Fisher information metric, which is the natural geometry for any statistical model. But then you add this second term, h, which actively warps and deforms that space based on three critical system-wide properties. And these are the three magic ingredients, the conditions you have to meet. For a stable geometry for intelligence to even exist, the system has to cross critical thresholds. For integration, meaning you can't break it down into smaller, independent parts. Coherence, meaning its components are all synchronized. And differentiation, it has to have a rich variety of possible states. If you fall below these thresholds, the geometry just collapses. It's a phase transition, just like water turning into ice.
Okay, so this is where the theory gets real. To actually operate under these new geometric laws, the paper proposes a completely new kind of machine, a hybrid classical quantum architecture, built from the ground up to respect this geometry. So the classical part of this machine is something called a hyperbolic neural cellular automaton. Forget a flat grid, the cells here live on a curved hyperbolic plane. And why hyperbolic? Well, it's simple. Hyperbolic space has exponential volume growth. It's the natural container for the exponential data we were talking about. This architecture directly solves the capacity bottleneck from Theorem 3.1.
But here's the really clever part. How do you measure those global properties, like coherence, in real time to control the geometry? Classically, that's almost impossible. So the architecture uses a quantum coprocessor, not to run the model, but to act as a ridiculously high-speed sensor. It can measure the entire system's global topology in milliseconds. A classical computer, it would take minutes.
And that 100 milliseconds, that's the magic number. That is a feedback loop fast enough to allow the system's global geometric state to guide and correct its local updates, all in real time. It's operating on the same timescale as biological cognition. This isn't just about being faster. This enables a completely new type of computation.
All right, the theory is elegant, the architecture is wild, but does any of this actually work? That brings us to the experimental showdown, where this geometric theory is put to a rigorous, falsifiable test. So the experiment is simple, a head-to-head showdown. System A is the new architecture with all the geometric feedback turned on. System B is the exact same architecture, but without the feedback. It's a zombie control. And the results? They are absolutely undeniable. Across every single metric, generalization, topology preservation, coherence, the geometrically regulated system just blows the control out of the water.
Let's just zero in on the most important metric here, generalization to data the model has never seen. System A hits nearly 88% accuracy. That's a massive 23.4-point jump over the control. This is not some tiny incremental improvement. This is a giant leap in robustness, and it's the practical proof of this geometric approach.
Now this is a slide that proves causality. The researchers measured how differently the two systems actually learned over time, tracking their paths through the solution space. That final number, 47.3, means they took wildly different paths. This is a greater than 20 sigma result. In statistics, that's basically absolute proof that the geometric feedback forces the system down a completely different and fundamentally superior learning trajectory.
And what about efficiency? Check out this number. Remember how the theory predicted a path of least resistance, a principle of least action? Well, the experiment proved it. The geometric system finds its solution using a learning path that is 3.2 times more efficient, or lower action, than the control. It's not just better, it's smarter about how it gets there.
So, what does all of this mean in the grand scheme of things? Well, the paper's conclusion takes this from just a new architecture to a universal principle. It's proposing a grand unification, framing intelligence itself as a kind of field theory, governed by the same sort of mathematical laws that describe physics.
It all boils down to this one beautiful unified action principle. Just like a ball rolling downhill will always find the path of least resistance, the system's entire behavior, learning, adapting, all of it emerges from a single, simple goal: minimize this one quantity, S, over time.
And this action is really made of three key parts. The first part is just standard Bayesian inference, basically minimizing your prediction error. The second part is informational gravity. Yeah, you heard that right. It's formally identical to Einstein's equations for spacetime, where information literally curves the cognitive space. And the third is a topological term, enforced by that quantum sensor that makes sure the system's global structure holds together.
And all of this leads to a really powerful and honestly a pretty provocative conclusion. The era of just kind of sprinkling geometric concepts on top of existing deep learning models is over. What this research is proposing is a fundamental paradigm shift, a complete field theory of intelligence where the geometry isn't just some feature, it's the central organizing principle. Look, this isn't just some abstract theory. It's a direct challenge. The whole framework is built on falsifiable predictions, and that divergence test is a clear, hard benchmark. The paper lays out all the math and the experimental proof, so the real question for the entire field is, who's going to replicate it first?